We used to buy personal computers to serve as glorified typewriters that occasionally stream Netflix. Nvidia is dropping the RTX Spark chip and turning laptops into autonomous silicon employees that might eventually demand a salary and a comprehensive dental plan. Pulling from PC Mag, Tom's Guide, and Microsoft's Windows Experience blog, we are dissecting whether Nvidia's aggressive push into ARM-based processors is an actual threat to Apple's MacBook Pro or merely a high-priced vehicle for generating AI video slop at unprecedented speeds. Realizing your standard 5-pound backpack now contains a device with more processing power than the server farms that ran the entire early internet is genuinely disorienting.
Fusing a massive central processor and a high-end graphics processor into a single 3-nanometer system on a chip completely changes the fundamental physics of the motherboard. The RTX Spark packs a 20-core Grace CPU alongside Blackwell architecture featuring 6,144 CUDA cores.
Hearing 3-nanometer and 6,144 CUDA cores sounds kind of like reciting a spaceship manifest. What does shrinking a chip down to 3 nanometers actually do for someone typing an email or watching a video?
Cutting the physical distance electricity travels reduces the required voltage to push the signal across the board. Less voltage translates directly to, drastically less heat generation. Nvidia squeezed the underlying logic from their massive DGX Spark desktop workstations, the massive metal boxes used by animation studios, into a physical footprint sitting comfortably on an airplane tray table.
Manufacturers usually compromise on memory to save space during that fusion process, but the spec sheet lists up to 128 gigabytes of LPDDR5X unified coherent memory. Seeing 128 gigs of memory in a consumer laptop feels sort of like a typo. Most high-end desktops barely run 32.
Having 128 gigs of unified memory means rendering a 4K video while keeping 400 browser tabs open feels like walking through an empty park rather than fighting your way through a packed rush-hour subway car.
Wait, cramming 6,144 CUDA cores into a half-inch chassis sounds like a rapid way to melt the plastic keys off the board. Normal people do not need desktop-grade Blackwell GPUs to send emails or read the news. This sounds like battery-draining overkill.
Operating on a sliding scale of power consumption prevents the hardware from catching fire. The chip drops down to single-digit wattage when you are scrolling through text on a website.
So it sips power like a basic tablet.
Ramping up aggressively to 80 watts happens the second you hit it with a heavy compilation workload or load up a modern video game. You get the battery life of a smartphone and the brute force of a desktop tower inside the exact same machine.
That dynamic power scaling serves as the engine for what Nvidia calls Agentic AI. Moving past traditional applications means entering an era where the computer runs massive local AI models directly on the hardware without relying on the cloud. Tom's Guide ran extensive hands-on tests on the Computex floor, hooked up to a multi-device OpenClaw setup, running alongside the News Research Hermes agent.
Watching an AI agent take over a web browser, independently navigating pages, and filling out complex corporate forms in seconds makes manual operation obsolete. You become a manager watching the cursor move on its own.
They also demonstrated a creative tool generating a 3D animated griffin from a simple sketch using Comfy UI. Tom's Guide specifically noted the bird's legs kept hallucinating and disappearing entirely during the animation cycle. Building the most powerful laptops in human history just to generate low-quality video slop faster feels like a massive misallocation of resources. We are inventing supercomputers to make fake birds that cannot even render their own feet.
Dismissing the entire architecture because of a glitchy Griffin demo ignores the actual stakes of localized processing. That specific workflow functions as a public proof of concept for absolute data privacy.
Because everything stays local on the machine.
Processing the AI models locally on the hardware ensures your proprietary sketches, your financial documents, your private emails, and your medical records never travel to a corporate cloud server. Security functions as a physical hardware boundary. Relying on software promises becomes obsolete. Corporations cannot scrape your personal workflows to train their future models when the data never leaves the metal box sitting in your lap.
Apple built an entire modern empire on the exact promise of powerful, unplugged privacy with their M-series chips and the new MacBook Neo. They established the benchmark for laptops that deliver massive performance without dying before lunch. Nvidia is matching that battery efficiency while aggressively attacking Apple in the gaming sector. Running native ARM games like Alan Wake 2 using DLSS 4.5 ray reconstruction and emulated games like Pragmata at over 100 frames per second at 1440p resolution reveals the exact nature of that threat. Pushing 100 frames per second on battery power used to violate the laws of thermal physics. Gaming on a MacBook feels like trying to off-road in a golf cart. The hardware fights you every step of the way and you eventually just give up. The RTX Spark feels like an all-terrain vehicle that flat-out refuses to be tethered to a wall outlet. How is it getting a massive game like Alan Wake 2 to run smoothly without draining the battery in 20 minutes?
Ray reconstruction guesses the lighting and reflections using AI hardware rather than calculating every single pixel manually. The GPU renders a lower resolution frame, and the specialized AI cores use their trained models to fill in the missing visual details instantly.
That offloads the heavy lifting.
Lowering the computational load keeps the power draw low enough to run a massive graphical environment off a standard lithium-ion battery.
Reaching that graphical fidelity without plugging into a wall requires laptop manufacturers to abandon the bulky gaming aesthetics of the past decade. The industry is currently waging a petty war over fractions of an inch. HP claims its OmniBook X14 is the thinnest laptop on the market at 0.53 inches thick. Asus immediately undercuts that claim by launching the ProArt P14 and P16, measuring just 0.51 inches thick. Shaving off microscopic layers of aluminum just to claim the crown for a press release seems entirely superficial.
Altering the thermal dynamics of the entire machine forces manufacturers to completely redesign the internal cooling fans and vapor chambers. MSI is pushing the physical boundaries further with the Prestige N16 Flip AI plus AR functioning as the first RTX Spark 2-in-1 device, featuring a massive 16-inch tandem OLED screen.
Stacking two separate light-emitting layers on top of each other doubles the peak brightness without burning out the individual pixels over time.
Pushing into weird aesthetics, MSI is also releasing a highly specific Vincent van Gogh edition of the Prestige 14, plastering classic art across a high-performance machine.
Microsoft is jumping into the premium space with the Surface Laptop Ultra, utilizing a 15-inch mini-LED pixel sense display, hitting 2,000 nits of peak brightness. Staring at a 2,000 nit screen indoors feels, kind of, like looking directly into a high-beam headlight. The tech industry is trying to smuggle an autonomous, world-changing intelligence into our homes by disguising it as a boring half-inch silver rectangle.
Quoting Nvidia CEO Jensen Huang directly explains the strategy behind those designs. He stated they want users to go on the journey at your own pace. Wrapping a radical AI architecture in a familiar external chassis prevents consumers from experiencing profound technological shock. Handing someone a device that looks exactly like their old college laptop prevents panic when it starts executing multi-step workflows entirely on its own.
Microsoft had to rebuild parts of Windows 11 for this hardware launch. Rewiring the core of an operating system sounds like a massive vulnerability. How are they managing 20 different processor cores without the system crashing constantly?
Integrating workload profile scheduling allows the Windows scheduler to dictate tasks across all 20 of those cores with extreme precision. The new scheduler actively monitors your exact workflow, routing heavy calculations immediately to the high-performance Grace cores and pushing background data syncing to the low-power efficiency cores.
They also deployed the Microsoft Power and Thermal Framework. Calling it a framework sounds like corporate marketing. What is it physically doing to keep a 0.51-inch laptop from melting into your desk during heavy workloads?
Continuously pulling the microscopic temperature sensors embedded throughout the chassis turns the software into an active thermostat. If the graphics processor spikes during an intense video render, the software instantly reroutes power away from the central processor.
It actively starves the CPU to keep the shell cool.
Throttling individual components in real time maintains the external temperature of the aluminum shell. The machine dynamically balances its own heat distribution so the user never feels the spike.
Emulation usually creates massive lag. Running a game designed for one type of processor on a completely different architecture normally drops the frame rate to zero. How did Microsoft fix that for competitive gaming?
Upgrading the Prism emulator with AVX and AVX2 instructions sets support functions like handing a massive new dictionary to a live translator. Legacy games, anti-cheat software, video editors, and heavy creative apps rely on those specific AVX commands to render physics and process audio.
Translating those complex commands word by word bottleneck the processor on older emulators.
Understanding the entire phrase instantly removes that bottleneck. Adding that dictionary means anti-cheat software, like Epic's Easy Anti-Cheat, runs smoothly on the ARM architecture without triggering false bans. That compatibility issue has historically been the massive wall-stopping competitive gaming on these types of machines.
Riot Games is bringing Valorant and League of Legends directly to the platform because they know the emulator can finally handle the security layers without lagging.
Expanding the application ecosystem proves this is a permanent architectural shift. Developers utilize CDA-accelerated PyTorch and TensorArt directly in Windows without needing a massive desktop tower. The creative pipeline no longer requires being chained to a heavy workstation.
We are shifting from clicking buttons to delegating complex tasks. The relationship with the computer completely changes. You provide the high-level intent, the hardware handles the tedious execution, and you review the final product.
Delegating entire workflows to a local agent redefines modern productivity. You hand the computer a directive, and it acts as an autonomous extension of your own capabilities.
If your laptop becomes an autonomous agent that actively writes your code, answers your emails, and edits your videos locally, who actually owns the rights to that output? You, the hardware manufacturer, or the ghost in the machine? Goodbye.